So good morning students, welcome back. Today we'll discuss application of Gauss theorem. As you know, last time we discussed Gauss theorem, and we know Gauss theorem is always applicable when charge comes in closed surface. Okay, so whenever the charge comes in closed surface, it releases electrical flux, and that amount of releasing flux is given by phi equals to Q by epsilon naught. Okay, it means the releasing or emitting flux over the closed surface is 1 upon epsilon naught times the total charge. Okay, so we did that time. Okay, now students, look, today we'll discuss its application. Generally we are having 3 applications. Now first of all, discuss the first application. Let's start. Electric field due to an infinitely long straight charge wire. Okay, one of the most important application for board's point of view. Okay, look students, let AB, this AB is a long charge straight wire. Okay, that is a small part of long infinite charge straight wire. Now it is charged, but charge is open, and we know Gauss theorem is always applicable when charge comes in closed surface. So what we'll do, students, we'll assume a cylindrical closed surface around this straight wire, and this closed surface is said to be Gaussian surface. It is said to be Gaussian surface. So around this wire AB, we'll assume a cylindrical closed surface, and this cylindrical closed surface is said to be a Gauss surface. Now we can apply Gauss theorem, because Gauss theorem is applicable when charge comes in closed surface. Okay. So now students, around the wire AB, we assume a cylindrical surface, and that is said to be a Gaussian surface. Now students, we'll find electric field at certain point P. Look students, so when charge comes in this closed surface, it releases electrical flux. This release electrical flux, and how much flux will release from this closed surface? That is given by Gauss theorem. Phi equals to closed integration of E dot ds. That much flux will release from the closed surface. Okay. Now students, see, this cylindrical surface having 3 portions. Actually, flux will release from 3 different paths. Flux release from this path. This is said to be, we'll assume this as first circular path. This will release electrical flux. This is second circular path, that also release electrical flux. And third and last one is, this is curved path. Okay, this is third curved path, that also release electrical flux. So what we'll do, students, we'll divide E dot ds in 3 parts. This is flux releasing from total surface of this cylinder. We'll find individually from first circular path, from second circular path, and from the third curved path. So what we'll do, students, we'll break E dot ds in 3 parts. E dot ds plus closed integration of E dot ds plus closed integration of E dot ds. This is the releasing flux from first circular path. This is the releasing flux from second circular path, and this is the releasing flux from this third curved path, the middle part. Now students, whenever we remove dot by the property A dot B equals to AB cos theta, scalar dot product, we'll use EDS cos theta, EDS cos theta, and EDS cos theta for first circular path, for second circular path, and third for curved path. Okay, this is third curved path. Now students, the most important thing, angle theta. How can we take angle? Look students, suppose this is a point P. How can we find the direction of electric field at a particular point? We have to put there a test charge. Okay, so plus, repel that plus. So this will be the direction of electric field for first circular path. And what is area vector? We know students, area vector is always normal to the surface. So area of this is in upward direction normal. It means at circular path E and ds are perpendicular. So for first circular path theta should be what? 90. So here I am going to write 90 because E and ds are perpendicular. Similarly, at another second circular path, area is normal downwards to the surface, normal upward to the surface, and here downward to the surface. And this is same we can find by putting test charge direction of electric field. Okay, that side again it is perpendicular. So write 90. It means at a circular path E is perpendicular to ds. So we use theta as 90 and 90. While on other hand, at curved surface, okay, this is the test charge plus repel to that test charge. So this is the direction of electric field. First arrow is indicating the direction of electric field, and its area vector is that side. Okay, normal to the surface. It means at curved side, E and ds are in same direction. So at curved path, E and ds are in same direction. So theta should be 0. Okay, now students, we know cos 90 is 0, cos 90 is 0, and cos 0 1. So it remains only E ds. E is constant, electric will come outside from the integration, and there comes only integration ds. And finally, integration ds means what? Surface area of this Gaussian surface. Curved surface area of this Gaussian surface, that is cylinder. And you know, the curved surface area of a cylinder is 2 pi r h. But here we took length as L. So there comes 2 pi r L. So phi, how much flux will release? Phi equals to E into 2 pi r L. That flux from release that from closed surface. Phi equals to E into 2 pi r L. That flux released from this Gaussian surface. Okay. Now students, again we will applying the Gauss theorem. What is final form of Gauss theorem? Phi equals to Q by epsilon naught. We'll make some small change. Charge lies on per unit length of wire. Charge lies, that is charge Q, length L. Charge lies on per unit length is said to be linear charge density and represented by this sign lambda. Okay, so now students, charge Q will come as lambda L. So here I'm going to put lambda L. So finally, this is flux, okay, releasing flux, and that is also releasing flux. When left hand side equal, right hand will also equal. Compare equation second and third. Okay, we'll write E into 2 pi r L will equals to lambda L upon epsilon naught. L to L cancel out. Okay, 2 pi multiply with epsilon naught lambda, and r comes in denominator. Okay, so we got the first form, 1 upon 2 pi epsilon naught lambda by r. Either for getting the main form, multiply and divide by 2. So when we multiply by 2, 2 2s are 4, it becomes 4 pi epsilon naught. 2 into lambda, 2 lambda by r. And now since we know 1 upon 4 pi epsilon is called K, electrostatics constant. So E equals to K 2 lambda by r. That is electric field due to infinite long charged straight wire.